I have some notebooks today. Eh?
Yep.
Is your computer volume on? Do you want to try saying something?
Okay, sure. Does this work okay? Can you hear? I can keep talking. Would it?
Yes.
Okay, sure. Does it make? Try it with headphones or in another room or something. Oh, you're connected. Hello. Do you want me to keep talking? Can you hear it okay? Is there something that needs to get done?
Okay, I'll Can you say something?
Yes, sure, of course. Is this working okay? Can you hear? Okay. Maybe we got a couple minutes. Hey.
Brad wants to make an announcement first.
Okay.
I like your plasma physics Hamiltonian references.
Oh, this stuff is great. Do you know Phil?
Yeah.
He's
Did you work with him?
no, I never have, but I go to Woods Hall all the time, and you know he
Yeah.
lives there in the summer. So
we haven't overlapped at Woods Hall. Interesting.
no, yeah, I live nearby, so I've never spent the summer there, but I
Okay.
drive out for the day. I was there most of 2019,
Okay.
and then I haven't been back since. And I was going to go this year, but
Yeah, I know.
hard to be in two places at
Well,
once.
I'm glad you chose us.
Yeah, no, it's this is a nice opportunity. So no, I really love that stuff. I was excited to see. I hadn't seen that reference. So there's another one too. Salmon, do you know that one?
Rick Salmon.
Yeah.
I decided not to put that one in too. I think it's really good too.
Yeah, that's the one I learned it out of from I think
Yeah.
Brad or probably Steve actually. But
Yeah, I think Rick did a lot of the original work.
yeah. It's a more difficult reference to
and
dig up,
Phil.
as I recall.
Yeah.
Um,
I think Ted is a little bit clearer.
yeah, I think that's. I just flipping through it. I was like, oh, maybe I should look at
But
this.
we won't even mention Darrell Hall.
Well, yes. I teach Hamiltonian mechanics almost every other year, I guess. And so I spend a lot of time thinking about stuff that undergrads can do that isn't just like a hoop rolling down, like the sort of standard, like calculate the Lagrangian of this thing nobody cares about.
Well, I should bend your ear about it. I'm looking for a Hamiltonian.
Oh, cool.
So for those of you who want to hike up to dessert instead of taking the bus, a number of us are going to meet at the Gregory Trailhead at 5 p.m. You can find the directions on Slack or just do Google search for it. Of course,
I would suggest 4:30. It's an hour and a half hike.
No, but he's saying from the trailhead. From the
Well,
trailhead.
on the trail.
Yeah, it takes about 45 minutes to get there by foot. So of course, if it's pouring or it looks like it's bad thunderstorm, we're not going to do that. We'll just take the bus. But if it isn't, then you'd like to join us, please meet at this trail.
Well, thanks for coming
Okay,
back
cool.
for lunch this afternoon. Chapter 2 of Dedalus with Jeff Oishi.
All right, thanks. I will leave this up as long as I can. All right, so last time we spent some time thinking about the spatial discretization, right? So we're interested in solving PDEs, and very often we're interested in thinking about PDEs that evolve in both time and space. Now, given the nature of the universe, we're never really interested in studying PDEs that are only dependent on time, but we are often interested in studying PDEs that are only defined in space. So that's why we start with the spatial discretization. It's also, in some sense, one of the more complicated parts, and it's also the one where numerical methods differ the most. So just to remind you, we're talking about this framework that is a spectral framework called Dedalus. There are many other ways of solving PDEs, and they all have strengths and weaknesses. And one of the things about this, people get into giant arguments about what method is better. And the reason, of course, why people get in so much arguments is because they're all kind of equally bad. All right. And they have advantages and disadvantages in different situations, but as general tools, right. And that's somewhat surprising. Now, that said, there are assuredly wrong ways to do things, right? But there's no right way to do things, generally speaking. Now, so all the stuff that we talked about yesterday, spectral series and expansions, thinking about derivatives, everything I said about derivatives can also be, by the way, is not unique to derivatives. You can apply the same thing to many other types of linear operators. So for example, integration, if you need to calculate integrals, Dedalus provides that, .integrate on any field. And it does it by constructing a different matrix that does the same thing. Interpolation, right? Another thing we didn't really mention at all, in fact, but one of the early motivations, and in fact, one of the things that Chebyshev polynomials are used for in non-PDE land, in mathematical fluids, is interpolation, in fact, right? And so when you think about it, the reason why they're so good for interpolation is if you define a function as a series of coefficients expanded on a set of basis functions, right? If you have data, well, by definition of having data, you've got them at some discrete points, right? We're going to be talking a lot more about this, right? Where this is x, and we can call this x0, x1, x2, x3, and so on, right? So these, let's do this, shall we? Just to make clear that those are the data points and not the indexed locations in our domain. Okay, right? And so, sure. So here's our f of x by data. This is all we've got, right? If you're digitally sampling something, this is what you get. If you're simulating something, somehow it's discretized, right? Okay, so of course, what your brain does, and probably your most favorite plotting software will do, is that, right? By default, it'll probably even draw a line. That line is a lie. Now, it may be a small lie or a big lie, right? And how big or bad a lie it is, if this is all the data you have, you don't really know, right? And so the point here is if you discretize things on a grid and you choose the right grid, important, right? And you go back to your basis functions. Now, when you go for the transform of taking these grid points and calculating the spectral coefficients from that sample data set, well, now you have this representation, right? So you get 1, 2, 3, 4, 5, 6. You've got 6 variables, so you're going to end up getting right? Typically, for most basis functions, we include the 0 mode for reasons which we'll get to later, right? So this is going to be defined on this. So you got a column vector of 5 numbers, right? But if we've spectrally expanded it on this basis function, this function is a known analytic function that we like and that we can compute cheaply and easily. So that means that if we want to find the data here, right, we can simply, we've got these, we reconstruct this way, and now we can simply evaluate our basis functions at whatever point we want. We have interpolation, right? So that's actually what Chebyshev polynomials are widely used for in domains that don't involve PDEs. Okay, so that's kind of where we left off, right? So that idea of interpolation, of integration, of differentiation, all of these things can be expressed as matrices, which we can then use linear algebra software to do. And we like to do that because people have made a lot of money with linear algebra software, which means that linear algebra software is pretty good, right? We want to take advantage of that. All right. So that kind of, at the end of last time, we sort of spent a lot of time talking about how this works. And remember, if we think of our canonical form of our PDE, right, where this n is a function, could be nonlinear. By the way, when I say nonlinear, I do mean that not in the sense of necessarily of higher than order 1 in the variables, but also order 0 in the variables, right? We'll come back to that later. But for example, if you wanted to do a differential equation that in Dedalus looks like this, right? I don't know why 6, but presumably that 6 has some meaning to you. This is an affine term, right? It does not depend on the independent dependent variables. And therefore, we cannot put that on the left-hand side because it is in fact not linear, right? When I say linear, I mean in the usual definition. So there are like 7 rules that define a linear space, and you can find them online pretty easily. Okay, I'll put them in the lecture notes, but I'm not going to write them now. Okay, so that's the idea. When you have it in this form, what we're going to talk about now is this part, the m terms, the time derivative terms. And so what you can think of is once we've done this discretization, we've turned all the spatial parts from continuous in space to discrete in space. And you can just think of them as solving for the spectral coefficients now, right? If I just turn this like that, right? Now these are simply a whole bunch of coefficients that evolve only in time. We can use any ODE solver we'd like. So I'm going to talk a little bit about ODE solvers, very little bit. And I'm going to point you in a couple of directions. And then we're going to get down and do some actual practical playing around with the software, which is a big part of all of this as well. Okay. Yes, of course.
I missed the linear part is fine.
Yes. Yes.
The nonlinear part now has strongly coupled.
Correct. That's right. That's right. So I haven't talked about the nonlinearities yet, but we do them. The trick basically is we do, and I'll talk about this later, we do what's called the pseudospectral method, which means that we take them from grid space into, from coefficient space into grid space, where the nonlinearities are simple multiplications, right? And then we transform back. And there's a little bit of a caveat that you need to know about that, but we'll leave that for now. That's the basic idea. So this is going to go, when we do the time stepping, we're back in coefficient space and all the nonlinearities have been evaluated in real space or grid space. Okay. I'm going to avoid trying to use the word real space as much as I can possibly do. But when I say that, I mean the space on the grid, as opposed to the coefficients. That's right. That's right. Right. So this is grid space. This is coefficient space, the hats.
What do you mean by now we go to ODE solve? I mean,
Okay.
it's first order differential equation.
It's not necessarily first order. Oh yeah, they're all going to be in first order form. That's true. Yes. They're going to be first order in time. So all of this, everything else is going to have been discretized. And so all that's left now is going to be solving the equivalent of something like, for each mode n, each coefficient n, right? There's going to be a whole bunch of stuff. And this, now all of the stuff, because we've discretized away all of the spatial derivatives, now these are all ODEs, because it's just the evolution of each of these components that depend only on time. Right, and so that's the idea here, is we've separated variables on time here. Now the trivial thing to do when we go to multi-dimensional problems, which basically are the same as one-dimensional problems except more complicated and expensive, right, is we could either separate those variables. For example, we could add a Fourier basis in Y, so now we have a two-dimensional problem, right? But that all of this stuff, the time is always separated. We might also do some non-separable basis functions over here that are multiple dimensions but are coupled, right? Spherical harmonics, polynomials in various different forms that allow us to do different kinds of things. Okay. But time is always separated off for this reason. It allows us to use very well-established ODE technology. This sometimes is referred to as the method of lines. You will hear that occasionally. All right. So I'm only going to, in the lecture here, I'm only going to cover 2 solvers, and I'm only going to cover 2 solvers that you should never actually use in practice. And the reason is relatively straightforward, and I'll get to that in a second. Okay. All right. So given that we've discretized and we want to solve our ODEs, like I mentioned at the end of the last time, let's consider the simplest right. This is the one that, if you think about it for a few minutes or less, right? I've avoided writing H to try to keep this as close to our subject matter as possible, delta T, right? Well, if you want to approximate this numerically, the simplest thing to do is, well, what can I not do with a computer? This. I can do all the rest of this with a computer. So we'll just throw our usual caveat on there, right? And if we're doing theory, we'd be done. This is true. This is true as long as delta T is sufficiently small. Right, so this tells us that the way we can update one step in the future, let's call this some function g of t, right, which is df dt. Okay, and so we just this apart. Okay. This is the simplest possible ODE solver. It's the most obvious one, I think. And every other one is more or less some elaboration on this idea. That's why we're going to use this as our template, even though you should never actually do this. Okay, so now, of course, we're going to discretize in time as well. So we're going to take time to some time step, which is equal to n times delta t. We're assuming equal time steps for now. Everything I say can be trivial, discarded from equal time steps if you choose not to use them, which in many cases you should not. Okay, but there's nothing really, not too much lost by doing this. So what that means is now we can these, and again, right, n is defined on the integers. So these are integer discretized things. Countable infinity, perhaps. Okay, so now we're going to use just a little bit of notation here. So f sub n is f at t sub n, so that we can eliminate some of these things, because now it's not really a function anymore, it's discrete. It's more of a map. And so we call this the forward Euler time stepper. Forward Euler is fine for ODEs. It's not very good in terms of you need a very small time step in order to get accurate results. There are better ways of doing this. And in fact, for certain cases, there's a provably optimal number of steps that balance the number of evaluations of the function, right? Because if you made this more complicated, you could Taylor expand to a higher order in time, use those things, but then you're gonna have to evaluate G more times, right? That may be cheap or that may be expensive, depends, right? If it's particularly cheap, then you can do many more evaluations of it and you'll get a lower error as a function of dt. I'm going to go into the theory, the asymptotic theory of these things very much, in fact, not at all. but I will introduce one notation, which is to say this is called a first order time stepper, because the error is going to be proportional to dt. That's not good, right? We would like that to be higher, because if we made dt smaller, if this were, say, order dt to the fourth, that would be much better, right? Because if we doubled, if we halved our time step, we'd go down by 2 to the 4 rather than just a half in terms of our error. Yes. This is an initial value problem. So by definition, if you don't know, you can't solve it, right? You have to provide the initial condition. That's what we get here, right? So g of t or a function thereof, yeah. Yep, right? And then we have our data, right? We can evaluate g on that data, right? And then we get delta t and we get the next step. And then we can just roll this forward. So this is also thanks for pointing that out. This is also a self-starting method, right? If you have the initial data, you need nothing else. There are many time steppers for which that is not true. And we'll get to that in a second. Okay. All right, so this works okay for ODEs. Oftentimes it's not efficient, but it can work. It very often does not work at all for PDEs. In fact, it will fail spectacularly in many cases. And that's because there's an interaction between what these things on the left-hand side are and time, right? Because the spatial drifts can cause all kinds of interesting problems. Okay. All right. So this simple, is that there on purpose? Okay, so this simple ODE solver, like I said last time, I ended last time by mentioning the fact that we can divide our ODE solvers into two classes, implicit and explicit, right? And so explicit depends only on the past. So the simplest explicit scheme is the one we've seen. Okay. And the simplest implicit time stepper is the so-called backwards Euler method. Right, and there's the difference. Okay, so if you think about this for a second, if g is a linear function, then we can solve, this becomes a linear system. Right? By the way, everything I've written here is a scalar equation, but these also could be vectors. That's fine. And they could be coupled systems of ODEs. So each mode can couple to the others, and if it's nonlinear, they do. So this is a linear function. Then this becomes a linear system that we can solve, right? And that's why it's important to have nice sparse matrices, because we want to solve that linear system as cheaply as possible. Okay. And we get something for that price, which we'll see in a second. The explicit is much simpler, right? So if this is a nonlinear function, then you can simply approximate it once. This is no longer a system of algebraic equations, right? It's essentially just arithmetic. So you can do that very easily. Okay. So let's go back now. Now that we've kind of covered, you now know everything there is to know about ODEs. Let's go back to PDEs. let me just, a little bit of notation. Now, you'll notice this is still, I've written this as, this is not a mistake. This is a total derivative, okay? Because we've still discretized everything here and we're in discretized space. So this is now a representation of a PDE, discretized in space, left continuous in time for the moment. And you'll notice one thing here. This is what I referred to earlier as the so-called pseudospectral method, okay? We take that n term, the nonlinear function of our state variable. We transform it from coefficient space to grid space, where nonlinear terms are simply multiplications, right? If I have u dot grad u, I just multiply at every point on the grid the value of u times the value of du dx. That's an order n operation. If you have n data points, you need to do n calculations to do that. If you go into coefficient space and try to do the same thing, you will find it's an n squared computation to do that. So that's why it's worth, so is it worth it to go into physical space or not? Because obviously it's going to cost you something to get from physical space, right? From grid space, from coefficient space to grid space and back. And the question is, if you have a the question is answered, if you have a transform that is faster than n squared, then yes, you win. And this is why we don't just choose any basis functions. We choose basis functions that have nice transform properties as much as we can. Now, in the spherical geometry, we don't have them, and so we plug along with slow transforms. Okay. All right, so this hat means here over the whole thing means I take the calculation of the nonlinear function of my state variable, and then I transform that whole thing back as a piece of data, u dot grad u. Okay, that whole thing, now I transform that back one transform. Okay, and now we have a whole thing. This is our ODE. So let's project this in some sense. We're going to leave off the nonlinearity for now. We'll set it to 0 and analyze something in particular. So let's see how we might put this. How would we represent this linear operator, right, in such a way that we could characterize it? Now, remember, this is a discretized linear operator, and we've chosen a basis. So what is this object now? It's a matrix, right? So if we want to think about how is this ODE going to behave, we need some way of characterizing that matrix acting, right? Now, I'm not talking about actually solving it. If we're actually solving it, then we go off and do it, and we pay a computer to do it. I'm talking about thinking about it so that we can analyze, say, the stability properties of this ODE solver. We can make choices about it. And so it turns out that we can project this into some sort of ODE system, right? I've changed variables here just to show that I'm picking out one particular one, right? And I've turned this into this, and this, as it turns out, anyone want to venture a guess what this is? What's that? It's an eigenvalue, right? This right, of L, which is the discretized form of our operator. I'll use this double arrow to mean matrix. So why do we do this? Well, we needed to come up with some idea of the sort of size of this matrix. And we can do that in a lot of different ways. But for a given, if we have an inner product, that inner product on our linear space can induce a norm, right? And for us, the inner product is our So this is for a vector x, right? We take its dual, we project its dual onto itself. We take the square root of that. That's our inner product. And that gives us what we call the L2 norm. That's a measure of the length of the vector in some sense. From this inner product, that in turn can induce a norm on the matrices that we define on that space. The matrices on that space, remember, transform one member of the space to another. So if we have some matrix A, we write the matrix norm with 2 lines traditionally. This number 2 here is just reminding ourselves that we built this as off of an L2 norm. In practice, we never bother to write this because we always use an L2 norm. And that's defined as the max over all of our vectors x such that A acting on x divided by x maximized over all vectors in the space, that gives us the L2 norm. That gives us an induced matrix norm. And it turns out for the L2 norm, I mean, this seems a little weird, right? You have to find every vector in the space and figure out, test this against it. That's not going to, it's going to take a while, right? And it turns out though, for the L2 norm, we can write this in a special way. This is the so-called spectral radius of a matrix. And the spectral radius is the maximum, the biggest eigenvector, sorry, biggest eigenvalue over this matrix. So now all we need to do is find the eigenvalues of the matrix and pick the biggest one. Yes. Yes, correct. Thank you. Very important.
A star
Okay, so A here, A star is our Hermitian transform. So that's the conjugate transpose of the matrix times the matrix itself. If that's true.
If you don't use that, how would you distribute?
Knowing that A is a matrix, yeah, you could. I suppose it's true. You're absolutely right. It is very common in the applied math literature to use star for the matrix transpose. I agree with you. It is, in fact, better to use dagger for exactly that reason. And that's, yeah, it's worth thinking about that. Okay, so in that sense, the eigenvalue here, perhaps the largest eigenvalue or the largest, the eigenvalue with the largest magnitude gives us some sense of the matrix as a whole, right? And then if we think about what's the part that's going to give us the most trouble, the largest eigenvalue of this of our matrix that comes from our matrix that comes from the discretized linear operator. The noise is incredibly distracting. Okay. All right, so let's consider a very, very simple ODE, the simplest one. Let's think about how we can characterize it. And then we can compare the known solutions of this simple ODE against what happens when you use a time stepping method. You discretize it. Okay, I've switched signs. Sorry about that. Right. Pretty simple. Now, this is an eigenvalue of some matrix, which means even if it's a real matrix, only certain real matrices have real eigenvalues. This is an annoying fact, which is unfortunately true, which means that even if we started with real data, right now we need to be thinking about complex values of lambda here. So if the real value of lambda, the real part of lambda, is less than 0, right? We can define absolute stability domain of a numerical method. This is a concept that only exists when in numerics. The ODE itself does what it wants to do, right? And that is when we take f of n plus 1, right? And we say that that is less than or equal to f of n. This is called absolute stability. Now, if the real part of our actual ODE is less than 0, then we know that the solution better have this property, right? Because that will be true for any time step. All right. Let's make a diagram of what this looks like. Now, if we discretize this, then our equation would look like this, right? So the thing that we actually care about in the numerical analysis literature, this is almost always called Z because it's a complex number, right? And we can plot the complex plane here of Z. And let's think a little bit about what these solutions look like. Okay, so if we're sitting on the real line, somewhere in the right half plane, right? But we're sitting right on the real line, what's the behavior of the solution look like there? Exponential growth, right? So here, that's a thing we've become unfortunately familiar with recently. Yes, that's what it'll do. What about here? If I picked a point here, what's gonna happen? Good. Slightly more interesting, right? And over here, same thing, but just going the other direction, so who cares, right? Okay, now over here, if we pick a point like this, what happens? Decays. Excellent. Right. And here, at this point, of course, it just exponentially decays. That's what the solution will really do, right? So what happens? Now we expect everywhere in the whole left half plane, right? We expect this behavior, right? We would expect that I should be able to, well, that worked fantastically terribly. Unfortunately, what's also fantastically terrible is for a given ODE solver, usually you'll actually only get absolute stability, something like that. Which means if this gets more negative, right? So let's say you have a stronger decay, or perhaps you take a bigger time step because you are impatient, right? You will not get absolute stability for this particular time stepper. The shading that I've drawn depends on the time stepper. All right. Let's make this a little more concrete. That's fine for an ODE. And if you had just one ODE, maybe you figure, all right, I'll just take a smaller time step and live with it. I wasn't really going to go into that. We can talk about it. It depends on the time stepper. You can do the analysis of the time stepper and you can calculate this quite easily. It's actually just a straightforward property of the time step itself. Oh, I will write this reference out. The book by Asher from 2008 is an excellent reference for all of this stuff. Despite the fact that he openly hates on spectral methods, it's a very good. The ODE parts are very, very good. I'll put the details of that in the notes also. Okay. Back to PDEs. Let's go back to the heat equation, but we'll assume we've already Fourier transformed it. Right, so for the nth coefficient, I apologize here, these are not Chebyshev polynomials. This is the nth coefficient of the temperature, right? There are only so many letters. Okay, right, we have Fourier, this is in a Fourier basis. You can already start to see the problem here. The eigenvalues are k squared minus k squared times the diffusivity. So pick a time step, any time step. Now for all of these, sorry, should be kn, right? The nth coefficient, nth wave number. Kn is the wave number, right? So now, almost all the time when we're actually doing this kind of mathematical analysis, we assume Lx is always 2 pi, so k is just an integer, but perhaps you're interested in systems that are not length 2 pi. I don't know why you would be, but you can put it in here and calculate kx, right? Okay, so we've got our kx's. Let's plot this. Let's pick a time step, right? So in this case, z is going to be equal to minus kappa k squared dt. You pick any dt you want, and we plot the real part of z against K, you can probably see what's happening here, right? So at Kn is equal to 1, we have, let's also, for convenience, let's set the heat diffusivity to 1, okay? So then this is just going to be, the real part of Z is just going to be 1, right? 1 dt. I didn't leave myself anywhere near enough room here because you know the story here. It's quadratic, right? So you're going to end up with the real part of Z is just going to get bigger and bigger and bigger, or smaller and smaller and smaller, right? More and more negative. So no matter what you've picked, right? No matter if your time stepper has a finite radius of absolute stability, if you're solving a PDE, even a simple PDE, and you have a diffusive term in it, you will always violate that somewhere. What does this mean? This means, of course, how do you pick the total number of Ks that you have? You do that by the smallest scale, physical scale you want to resolve, right? And if you pick some scale, it's the smallest scale, then you can calculate a dt for it, but it's going to be proportional to K squared. So you're going to need to pick a very small time step to solve this problem. That's bad because this problem is a linear, constant coefficient, homogeneous PDE. Like there aren't really simpler ones. You're probably never going to actually want to solve this numerically. In about 5 minutes, you're going to solve this numerically. Okay, so this is bad, right? This is why if you oh, and by the way, let's say you're interested in the KdV equation, which has a third derivative in it. Well, that's just going to turn into K cubed, right? Or let's say you're interested in pattern formation, so you want to do Kuramoto's Shevchinski. That's got a fourth derivative in it. Now you've got K to the fourth. Like this is just getting bad and badder and badder. Right? Okay. Oh, haha. Also, everything I just said assumes that your grid points are equally spaced. But if they're not, say you want to like concentrate grid points somewhere because you have interesting regions and uninteresting regions, then everything I say here applies to the smallest possible grid space. That's even worse, right? This is not good. Now, if there were a way to restore the absolute stability domain to the entire left half of left half plane, we would like that very much. And there is. The implicit methods are absolutely stable. So, but as I reminded you yesterday, you only want to use the implicit time steppers if you have a linear problem, because otherwise you have to solve a nonlinear system of algebraic equations at every time step, which if you have a gigantic linear system is very expensive and you need a really good initial guess. However, of course, we want to have absolute stability and we also would like to solve nonlinear problems, right? And luckily, mathematicians have solved this problem. They are called implicit-explicit time steppers, and they're exactly what they sound like. An implicit-explicit time stepper is one that splits your system into things you want to be implicitly time stepped and things you want to be explicitly time stepped. And it turns out that very frequently we can use this to great advantage. Now, the traditional advantage, the traditional way that we think about this, and now you start to see a little bit about why we write all of our problems in our canonical form. Implicit on the left, explicit on the right. So that's the small burden we place upon you, the user, to split these terms how you want. Now, a term has to be linear to appear on the left-hand side. You cannot put a nonlinear term on there. You cannot put an affine term on there. There will be an error message. And we're not great at writing error messages, so it might not be the most obvious of things, but it won't work. I think that one actually is pretty helpful. You can put linear terms on the left-hand side. No problem. You certainly can. Right? And sometimes it's advantageous to do so. Not often, but you can. Okay. So sort of wraps up what I wanted to say about time steppers. Oh no, there's right. One more thing. Yes, question. Interesting question. So the question is, could you use Fourier or spectral methods in time, right? And the answer is you could, but it's very rarely done. For a couple of reasons, essentially two. One is the trade-off is not usually worth it, right? You have to have global information about time to be to do that, which is fine. I mean, but very typically, one doesn't have a boundary condition at the other end of time, right? Especially for interesting problems. And so it's usually more worth it to simply time step, march in time using a sort of more traditional ODE solver. Okay, so does that make sense? But yes, people have considered it, and there are probably applications. There are certainly papers in the literature you can find about it. I can try to dig one up. I've never done it myself. I'd have never even heard of anybody who's done it, but I do know that it is something that people have studied. Okay. Yes.
You can solve this equation. Minus k n squared t.
Yes.
I think the problems you're talking about is you actually are time stepping this.
Correct.
And then you
That's right.
calculate the exponential.
That's correct. That's right.
You need to do that because the other complexes of the equation are still-
Correct. You're absolutely right. Let's actually talk about that for a second, because that actually there's a whole class of time steppers, okay, that do exactly that. If you happen to know the solution to this, you can use what's called an integrating factor method, right? Where you just literally multiply by e to the minus this thing, that thing, this thing, right? And you can time step. There's no time stepping error for that, so long as the integrating factor is the correct solution, right? However, it is very often the case that only works if you're in the Fourier basis. So if you're Fourier and you have a pure diffusive term. So for example, simulation codes that work in fully periodic domains to study things like 3D turbulence at extreme Reynolds numbers very often do exactly that, because they know that the only term they ever have is viscosity, which looks exactly like this, but with u instead of t. Yes. Yes, you could. But then you run into the problem of calculating that matrix exponential. And it usually ends up being faster and cheaper to just use an implicit time stepper for linear systems. But you're right, you could. What I'm pausing is because I'm not 100% sure that that isn't actually what an implicit time stepper is doing for some approximation of the matrix exponential. I have to think about that. Yes. Right, that's right. So that you only use an integrating factor when you know that this is a positive definite. Absolutely. Yep. Right. And that's the point. So for us in Dedalus, so there are, if you want to do the biggest calculation of 3D turbulence ever done, I would suggest you pause before using Dedalus. That's not what it's for. If you wanted to do the biggest calculation of Rayleigh-Bénard convection ever done, and then Dedalus might be quite competitive, right? because you can't use integrating factor methods if you've got boundaries, because then you can't discretize this way, and you no longer have that pure solution to your problem. Okay. Good. Question? Yes. This is true for anything, actually. Oh yeah, the eigenvalue, that's right. That was just coming from the PDE. The stability this boundary has nothing to do with eigenvalues or anything else, right? The eigenvalue only comes in from the PDE that we've discretized. Otherwise, it's just a number in the ODE solver. Does that make sense? Yeah, Z is just whatever it happens to be. However, that comes to us from a linear calculation. The explicit part will still have to lie in this domain, but it's usually not proportional to the wave number squared or some higher. It's usually just linear in that. And so you're much better suited there in the explicit. It's not usually as big a concern. Okay. So that's the theoretical stuff. That's the sort of background. Everything that I just said can be applied to more complicated time steppers, all of which are essentially more complicated versions of the same idea, right? You take the data at some time, you do some combination of steps, and there, like there's implicit and explicit methods. Let's just take explicit for a moment to be explicit. Explicit time steppers themselves can be divided into two categories: the so-called multi-step methods and the multi-stage methods. The multi-step methods are things like Adams-Bashforth, you may have heard of, and the multi-stage methods are almost always just called Runge-Kutta methods, because those are. So Runge-Kutta methods take time A, right? And then they take steps in between. They sort of fractionalize that time step and do things at like half the time step and a quarter of the time step, and then add them all up in some way that cancels errors. And it's very cool, right? Nice thing about Runge-Kutta methods is if you only have data right now, you can start them up from a cold start. The so-called multi-step methods take data at Tn, Tn minus 1, Tn minus 2, all the way up to the order of that method, which means that if you're at T equals 0, you don't have T of minus 1, T of minus 2, right? These are not self-starting methods. So you need some other method, usually forward Euler, or, to get you those first couple of time steps. So you can use forward Euler for one, then the next one you can use a second order time step, then the next one a third, and up, and then you have three. Say you're using a third order system. Okay. All of this stuff I'm only telling you about because we have coded all of this into Dedalus, so you never need to think about it. If you choose a multi-step method, it will automatically start itself up using some sequence. However, if you go to restart it and you want machine precision of your solution, you need to save 3 time steps and not 1, right? Because if you restart from 1 time step, Dedalus will happily do it, but it's going to fake it with forward Euler and then so on and so forth, which will be different than if you continued all the way through. The multi-steps, the Runge-Kuttas, they only take 1 data set, so they're fine. Now, there are many, many time steppers that we've built into Dedalus because it's actually pretty easy to do new ones for reasons which we can talk about offline if you're interested. We've implemented most of the implicit-explicit methods you're likely to have heard of. The CNAB, the Crank-Nicholson Adams-Bashforth, that's very much not a good one to use. The so-called backwards differentiation formulas, the DFs, those are okay. Those are multi-steps. And then we have a whole fraction of Runge-Kutta methods. These are not the simple Runge-Kutta methods that you probably learned about in high school or college. These are implicit-explicit ones, so they're quite a bit more complicated. So they have rather than Runge-Kutta you may have heard of as like Runge-Kutta 2 or 4, right? These have 3 numbers: 4, 4, 3, 2, 2, 2. And that's because of the way the stages work with the implicit and explicit methods. Here's the thing. There's lots of choices. There are many things. Each one of these things costs different amounts, right? The number of times you have to solve the matrices, all of these different things. The higher order the time stepper, generally speaking, the more expensive it costs to take one time step. So you hope that you should be able to get take a bigger time step, proportionally so that you have lower error you end up with less cost. The reality of it is, here's the first open question I'm going to pose to you. For a real, nonlinear, strongly nonlinear system, maybe a turbulent fluid system, maybe something else, what choice of time stepper represents optimal performance for a given accuracy? So far as I know, there is no known answer to that. Right? We know the stability properties of simplified systems. We understand how these things work in very idealized cases. But we do not know the answer to that. And that is part of the reason why Dedalus has so many time steppers. One of the questions we set out to answer many years ago when we started this was that question. We got kind of distracted and it's never been examined. It's a really interesting question. And I think it has interesting ramifications. But nevertheless, that is the case. All right, so now I'm going to start, unless there are questions on that, I'm going to start in on the practical stuff. Practical point number one, while we're on the subject of time steppers, if you know nothing else, use Runge-Kutta 222. It's built into Dedalus. It's relatively cheap. We use it for a lot. It seems to have pretty good properties. If you know better, use something else. Okay. All right. So let's take a second here. And if you have downloaded the Git repository I posted to Slack earlier today, it's this one. You can find it here. So this is posted to Slack. It's in my personal GitHub. It's called BSS 2022 Dedalus examples. And it's got some notebooks in it and a single Python file. So if you go ahead and look in here, you will find 3 notebooks, 0, 1, 2, and a Python file called load_d3.py. So if you have it, you can follow along. If not, that's fine. There's a bunch of exercises that I posted inside these notebooks for you to try. So let's first get a practical hands-on feel for doing the stuff about spatial derivatives. So back to yesterday's lecture. Okay, so how many of you have used Jupyter notebooks before? Okay, a large fraction, but not everybody. So you'll need to, in your Dedalus Conda installation, you'll need to, so notice that I've activated my Conda environment, which you can tell by the fact that I have this here. Mine is called D3-dev. That's because I keep lots of versions of Dedalus around. This is part of why Conda is so useful in the installation instructions. I have a stable version that is to test against different things. And then I have the development one. This is where I go and break everything. Okay, so yours will probably just say Dedalus 3, which I think is the default in our script. And you get to that by doing conda activate Dedalus 3. Okay, so if you don't have it, you'll have to type pip install Jupyter. Jupyter is misspelled or spelled alternately. Jupyter. In case you're wondering where that spelling comes from, this notebook system is designed to support the Julia and Python programming languages, hence the name. Okay, so when you do that, it'll run for a little bit. Yes? The base environment is always where you start. And by default, the install script of Dedalus creates its own. The whole point of Conda is to isolate things. So if you use our script, our assumption is you don't want your environments to be messed. We create our own. You will. That's right. That's correct. I don't know the answer to that. You could try that. I don't know. I will say the one downside to Conda is, like so many modern tools, it is based on the principle of who cares about efficiency. So it just installs stuff multiple times. That makes sense in some cases, right? The whole point of Conda is to make sure that you have this version in this repository, sorry, in this environment, and that version in that. However, for simple things like, oh, I have Jupyter in that one, now I need to install it in this one, it's not the most efficient. Yes. Analysis, I'm actually going to make a strong recommendation that you should not use Jupyter notebooks to do your computations. You should use them for data analysis. They're pretty good for data analysis, but you should treat them, this is all my opinion here, you should treat them the way you treat scrap paper. If it's something you're actually going to use later, it's worth writing in a script that you can run on the command line. Because if you do it once, that's fine. But if you do it thousands of times, the Jupyter notebook model kind of breaks down. It's very good for introducing things like this. Okay. Okay. So once you've done that, you just type Jupyter space notebook in that directory, and you'll see something like this. Don't get too hung up on it if it doesn't work. We can chat about it afterwards, and you can do this. Okay, so then you'll click on notebook 0. Oh, by the way, your directory will probably look different from mine because I've run the, you won't have these 3 folders yet. In fact, you shouldn't have one of them at all. Okay, so the way the Jupyter notebook works for our purposes is simple. It's a beautiful idea. You can mix rich text using the so-called markdown standard, which is a way of typesetting things. It also includes a mostly complete LaTeX renderer, so you can type LaTeX equations in here. And then you can also embed code that can be run. Okay. The important thing to recognize about this notebook is that it is not like a spreadsheet. If you change something, it doesn't update all of the cells. That's important. Okay, the way you run a cell, you'll notice that a cell has got a blue line by it. That means we're in this cell. So this is a text cell. So if you wanted to edit this text, you double click on it and it'll turn into markdown, which is a pretty simple way of like typesetting stuff. And then if you hit Shift Enter, it'll run the cell, which in this case will typeset things. The code cells have in and brackets here. Okay, the number here is not a number of the cell, it's the number of the last time it was executed. So we'll run this, Shift Enter again, and we're importing NumPy, Matplotlib, and the Dedalus.public. That's our public interface for Dedalus. So whenever you're using it, all the time, import Dedalus.public as D3. Okay. I'm going to skip over the text. I'm going to just tell you what it says. So Dedalus 3 is based on a coordinate-free system. So what that means is you specify a coordinate system, you specify a distributor, which is a purely numerical thing that doesn't have a correspondent mathematical object, and then you define bases for each dimension of the coordinate system that you want. So here we're doing simple things. Sorry, this is coordinate. That is a Cartesian coordinate by default. So if you go ahead and run this, okay, let's look at what we're doing here. We pick a number of coefficients that we want to discretize our problem on, 64 here. We come up with an x coordinate, right, which is just coordinate. And we give it a name x. This could have been r or z or y or q or p. We want to do something fancy. This also could be not Cartesian coordinate, could be a Cartesian coordinate system, right? So like x, y, z. It could be spherical coordinates. It could be other types of things. So we define our coordinate. Then we define this distributor. So this is one of the few places where Dedalus tips its hand that this code can be run in parallel. Right? The distributor means if we're going to run this on hundreds of cores or thousands of cores or 4, right? We need to figure out how to distribute the problem across all of those cores. And so we always build a distributor. It's the object that we hang kind of all of the framework off of, in a sense. So we can construct this distributor, and we're distributing over this coordinates. One of the things about Dedalus 3 is it no longer requires you to solve things in simple domains, like simply connected domains. You can have multiple domains that are patched together. So for example, some work that people have been doing is a ball. So with a shell overlying it with different physics in the shell than they have in the ball. You can do all kinds of things like this. So the coordinates in the distributor are not necessarily as straightforward as they are here all the time. And then we have a basis. So we're going to do real data. So we're going to use a real Fourier basis on the x coordinate. We give it the number of modes we want and x. We have to give it bounds where we want these to be, minus pi to pi here, and this d alias. So the d alias is related to the spectral, the so-called pseudospectral method. We'll come back to it later. I just wanted to remind all of you that it exists. Okay. So that's our background. Then we're going to create a field. And the field is, the distributor is the thing that creates the field. So it's coordinating all of the pieces. It knows the coordinate system. It knows how that is going to be, how that data is going to be split up. Okay. Okay. So the field name equals t, bases equals x basis. You have to specify the basis because you can have fields that don't have a basis, a constant, for example. Okay, and you could technically argue that's not a field, but we want to give it a name so we can refer to it later. And that's all we're going to do for now. By the way, this is a scalar field by default. You can create a vector field by typing vector field here. Tensor fields of arbitrary order are also allowed. All right. Now, the key point, right, is that this is a spectral method. So we're always switching back and forth between coordinate space and grid space, C and G. We can define data like this. T, then it is brackets here with either G or C, single letter inside here. And then you can set that equal. And what that does is here we're setting a coordinate. So we're setting things in grid space on our field. Okay. So we can print that data and hopefully we get what we expect. I'm not going to count it, but you can probably imagine there are 64 ones here. Right? So what we did is we assigned a constant 1 to this data. Now we've used a real Fourier basis. So think for a second in your head, what are the coefficients going to look like? Okay. Got a picture. Hopefully your picture looks something like this, right? The first coefficient is 1 and all the other ones are 0, right? Because the zeroth polynomial e to the I0 is 0. Sorry, e to the I0 is 1. That's the constant mode. So that represents whatever the average is across the domain. Now, this is pretty obvious, right? For 64 coefficients, we can just print them all and look and see, yep, okay. They're all 0 except for 1. It did indeed. Yep. Yep. So that's right. So when you do this, see, transparently behind the scenes, Dedalus is doing whatever it needs to do to transform from coefficient space to grid space. There's an FFT hidden in there. That's correct. And if you want to get fancy, you can specify the FFT library. Yep, there's lots of different things that can be done. The backend libraries for doing that are actually growing. As we speak, one of the Dedalus developers is currently working on implementing a new transform library for spherical harmonics. So lots of stuff is happening back here, but we try to make it so that you don't need to worry about it until you need to worry about it. Okay. Now we are it's generally speaking not easy to do this. If with 64 coefficients, it's easy, especially when one of them is 1 and all the rest of them are actually 0. I want to point out this is rare. You should also already notice some numerical error creeping in. Where do you see that? Yeah, some of them are negative zeros. Interesting, right? But they're all actually 0. We sometimes call this hard 0. It's actually represented as all bits 0. I make this point a lot when I teach introductory computational science almost every single year, and the whole first 2 weeks is the following lesson. Floating point numbers are not the reals. Not going to say any more than that, but it's true, right? So in fact, most of the time, what that means is that we have to decide what 0 is, right? Okay. All right, so of course, looking at a whole list of numbers is rarely a good idea, but plotting them can be much more helpful, right? So here's a plot. I feel obliged to give this advice. Always label your axes. Always, 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 right? The most frustrated person in the world is you in the future. Okay, so let's play around. The X dash. Ah, yes, the X dash, thank you. That is a command in the matplotlib library that makes it do both align and X's. It's actually really useful when you have discretized data to put those X's on there, unless you're trying to impress people, in which case you leave them off, right? You can specify color, it doesn't have to be X, it could be O's or triangles. There's an enormous amount of plotting. This library is very complete. I think that's the only nice thing you can say about it. Okay. So here's a few interesting facts. For those of you who are familiar with Python, but maybe not be super up to date on it, I will use the so-called F strings for printing. This is a way of formatting string data. I think it's the most clean way to do it. So F in front of quotation marks, usual Python caveat, quotation marks are interchangeable, double or single, doesn't matter, as long as you close and open with the same one. F, then open parentheses, then you type whatever you want, curly brace, name of variable right inside there. That's it. And if you want to format it, you can do that too, using the usual format strings. Okay. So what do we see? The shape, okay, so T of C, this whole thing looks like to you, the user, a NumPy array. So if you're familiar with NumPy, every single thing you can do with NumPy arrays, you can do with these data. Many of the things you want to do with NumPy arrays, you shouldn't be doing with NumPy arrays. For example, calculating the average, right? Why? Because that will simply calculate the average on the grid, add up all the numbers and divide by the number of numbers. But you have a spectral series here, right? So you can do much better than that. You can actually interpolate and get the integral to the nth order polynomial solution correct. And this matters when you're doing quantitative work. Okay. But you can, and so, for example, the shape is the shape of the data. So in this case, there's 64 in both coefficient and grid space. That's interesting. Okay. So let's get the grid. Okay. The grid points. So the distributor, local grid, again, here now we're tipping our hand that this is parallel, right? Because if we've parallelized our program, processor number 1 might have X from 0 to 1, processor number 2 might have it from 1 to 2, and processor 3 might have it from whatever the next part is. I lost track of it, right? So if you want to get the grid points that you're working on, you need the local grid points most of the time. Dedalus does allow you to get the global grids, but that's fine when you're doing 1D problems and small problems. But when you're running like 512 cubed problems and you ask for the local grid, you're probably doing something that you're going to be sad about later. Which basis do you want it for? Right? We want it for the X basis. So this gives us the X grid. So now we can do some like put some more interesting data on this. So let's go ahead and put a sine wave on there. So np.sine x. NP is NumPy. This is our numerical library. Sine is sine. X is the grid points. So this is going to calculate sign on the grid points and assign that to each slot in the grid space discretized vector for Dedalus. Okay, we can plot the data and it looks exactly like we hope it looks like, right? This is very, very smooth, which it should be, right? How many coefficients do we need to represent this data? 1, right? Just 1, because it's just a single sine wave. We have 64 of them. So 64 grid points on something that we can interpolate using only one polynomial should look quite smooth. And indeed it does. All right. Again, transform. And now already you see why we like to plot stuff, right? Because it's really hard to pick out the one that's not 0, right? Because now this projects such that the numerical noise from the transform makes a lot of them not actually 0, but only 0 to epsilon to machine precision. So again, we plot it and we see what we want. Okay, 0, 0, 0, not 0, the rest of them 0. Yes, question. Why is it the 4th coefficient? That was just what I was going to say. So, all right, how do we order the data? Right? Okay, so it's sine mode 1, right? Okay, so there's a little bit of stuff, there's a little bit of concession. We work really hard to try to make Dedalus as close a map to from code to mathematics as we can. There are certain times where the level of effort that would take gets extreme, and this is one of those things. The 0 mode of a real Fourier series, there's only one of them, right? The cosine mode. There is no 0 sine mode. That doesn't mean anything. However, we keep that anyway. This is equivalent to keeping, so for those of you who have done complex Fourier analysis, you know that the first coefficient will always be real, right? But of course, it's really a pain to tailor around that such that you have a real number and then complex numbers for the rest of them. So we leave that piece there. Now this is a real Fourier transform. You notice those are all real numbers, right? This is, so we have actually, it's not doing e to the I in there. It's actually calculating sines and the cosines separately. So cosine of 0, sine of 0, cosine of 1, sine of 1, 4th coefficient. Make sense? Yes. Yes, there is. Absolutely. Yep. There's a complex Fourier transform that will do all of the things that you think it will do. For example, it'll have 64 complex numbers even for real data on the grid input because, right, it'll have Hermitian symmetry, all the usual stuff that you're used to for Fourier transforms. And in fact, in version 2 of Dedalus, we only had complex transforms. But this is actually surprisingly difficult to work out. Well, that's not quite true. It was surprisingly interesting to do it in a way that's consistent with all of our other bases. Okay. All right, so here's an exercise I'm going to leave you to do. Try something with multiple modes, predict what the spectrum should be. By the way, we call the series of coefficient values the spectrum. All right, now we know that the Fourier bases are nice. We know that their derivative matrix is diagonal, but we also know that they only work for periodic dimensions. Question? Oh, 5 minutes. Ooh, okay. All right, so I want to show you something really quickly, and then we'll stop. Let's take a Chebyshev coefficient. So we're going to create another distributor. We're going to create a basis. Notice we did not create another coordinate because we're still using the x coordinate, same coordinate. New distributor, new basis. Same bounds, same number of modes. We'll create a new field and a new set of grid points, right? Because now we want the local grids of the x basis, the Chebyshev x basis, not the Fourier. We're going to create another field on the Chebyshev x basis. Okay. Now, first thing I want to do is point out the grids. I've already run this cell, so you can see the plot, but I'll run it again. Okay. So all I'm doing here is I've plotted the, oops, the code is unimportant. What is important is the labels. So this is the grid points along x. On the top we have the Chebyshev. On the bottom, we have the Fourier. The Fourier grid points are equispaced between whatever and whatever, minus pi and pi. Okay? It includes minus pi, but not pi, right? Because it's periodic and those two things are the same, so we don't need a grid point twice. The Chebyshevs, as you can see, I've only plotted every other one to make it clear here. They're not uniform. The grid's not uniform. It's quadratically increasing towards 0. It also does not include the boundaries. The boundaries are not on the grid in Chebyshev. Okay, fine. So let's now take our Chebyshev field and let's put sign on the Chebyshev grid points onto our data. Okay. Of course, it looks exactly the same. But now let's look at the spectrum. Here's the number of the coefficient. Here is the temperature of the nth coefficient, right? These are now Chebyshev coefficients. How many of them are not 0? The answer is 10, right? Why? Because we're projecting a sign onto a set of Chebyshev polynomials. It takes us 10 of those to do the same thing that takes 1 in Fourier. Does that mean that Fourier is better than Chebyshev? Absolutely not, right? If you pick one of the members of the basis set and project it onto that basis set, you will always get one coefficient, right? If we did 2x squared minus 1, we would get only one Chebyshev, right? Because that's one of the Chebyshevs. Okay. The other point I wanted to make here is you'll notice that the coefficients kind of bottom out, right? This is what we call resolved. What does that mean? That means that the coefficients on the that we keep, right, hit round off. Can't do any better than that on a finite precision computer. And we use double precision because it's a good trade-off. And that's going to give us a round off plateau around 10 to the minus 16. Okay. All right. That's all I wanted to say. If you look in the notebook, there's some nice NumPy tricks to be able to quickly calculate how many of them are not 0. Of course, we have to specify that bigger than some epsilon. There's lots of structure in this. Notice something about these points, right? If we put a line in there, it'll become more obvious. Right? Notice something. These are Chebyshevs, right? So they're not signed, but there's a parity, right? Could you predict that? Yes. Should you use that? Maybe. Maybe. All right, I will stop there. Take any questions and then we'll continue tomorrow. You wouldn't generally ever do this. I'd have to think about that. You would never really do this in this way. You would usually create just one for the same. I had to do this because I'm using the exact same thing with 2 different bases. That you would very rarely do. If you had multiple domains that interacted in some way, then you might have multiple distributors. But generally speaking, you'll only have one. I only did that because we're in a notebook and I'm rerunning this to show you at the same time. That is the roots grid, correct. We do not use the extrema grid. Dedalus always uses the roots grid. So the question is this the roots grid? Chebyshev has 2 grids on which it is orthogonal, right? And has the nice properties when we discretize it. I talked yesterday only about the continuous part, but of course we're discretizing. There are 2 possible grids on which you have an optimal set of weights, and those are the roots grid where the Chebyshevs cross 0, and the extrema grid, which includes the endpoints. There's a choice that we make to use the roots grid, and we can talk about it if you're interested. It's not that interesting. But you say I can hear the sort of like, what if I want the value at the end, right? Yes, for boundary value problems, you can specify data on the boundaries and that will be spectrally interpolated properly. We only ever represent, this is only used for the pseudospectral calculation of nonlinear terms, right? Which we can do wherever we want and then interpolate properly. Yes, we actually do include the boundary. It's just not on the grid. So if you wanted to know the value at the boundary, you're not going to get it by printing the first or last grid point. You can get it by interpolating, by using interpolate. And that will give you the correct spectrally accurate value of the value at the grid point. I think that means it's time for a break.